We will be using trigonometric identities in this video. This is our first look at trig identities, but you will have seen several of these earlier on in previous units. So to start with, this first video we're going to be using the reciprocal, the quotient, and the Pythagorean identities only. And the reciprocals we've been talking about in our earlier look at trigonometry, so these should look familiar. Sine, its reciprocal is cosecant, and you see those here. Cosine's reciprocal is secant, you see those here. Tan and cotan are reciprocals of one another. And quotient identities, when we discussed the unit circle, we talked about this a little bit. Tan theta is equal to sine theta over cosine theta, and cotangent theta is the reciprocal of that, cosine theta over sine theta. And all of the variables here are x's. I usually use theta in place of that, but it really doesn't matter. And then you have the Pythagorean identities, these three here, that we'll also use later in this lesson. So these identities, what are they used for? They're used to evaluate trig functions, simplify trig expressions, and to solve trig equations. And we'll look at examples of all of those within this video. I will give you these identities. You should memorize them through application, but I will put those up for you on a quiz or test. All right, for this first example, we will be evaluating a trig function using the identities. So question says, if theta is a rotation angle that terminates in quadrant 2 and sine theta is 5 over 13, find cosine theta and tan theta. So we've used basic trigonometry to answer questions like this in previous units, but here we will use the identity. So again, it says use the first Pythagorean identity to solve for cosine theta. So they are referencing this identity right here. So we will write that here and then apply it. So sine squared, I'm using theta instead of x, plus cosine squared theta equals 1. So if sine theta is 5 over 13, then sine squared theta would be 5 over 13 all squared. So 5 over 13 all squared plus cosine squared theta equals 1. So we want to solve for cosine here, so we'll take this quantity and move it over. So then algebraically we get cosine squared theta equals 1 minus the quantity 5 over 13 all squared. So coming up here, that would give us cosine squared theta equals 1 subtract 25 over 169. So that's just squaring. 5 squared is 25, 13 squared is 169 here. So we have a fraction here and a whole number here, so we'll rewrite this as a fraction. So that would be equivalent to 169 over 169. Subtract 25 over 169. And we get cosine squared theta is equal to 169 minus 25 would be 144 over 169. So 169 minus 25 is 144. That's where that's coming from. And then if you notice, we have cosine squared theta, so we need to square root both sides. So we'll do that, square root both sides. And we get cosine theta is equal to, the square root of 144 is 12. The square root of 169 is 13. And then we took the square root, so we need a plus or minus symbol here. So plus or minus 12 over 13. One clarification too, cosine squared theta, let's talk about what that really means. That means this, it means cosine theta times itself. Okay, that's what cosine squared theta. Sine squared theta means this. It means sine of theta times sine of theta. That's what those mean, just so we're clear. Okay, there are two answers to this equation, plus or minus 12 over 13. Explain how you know how to use the negative solution. So we have this plus or minus here giving us two answers, but we are in quadrant 2 and cosine is negative there. So cosine theta has to be negative 12 over 13, and we could say that in quadrant, abbreviate, quadrant 2, cosine theta is negative. It can't be positive. The cosine value in quadrant 2 is always negative, and we discussed the quadrants in which trig functions are positive and which ones are negative earlier in the year. Use a quotient identity to find tan theta. So Going up here, quotient identity, they're talking about this one right here. Tan theta is sine theta over cosine theta. So tan theta equals sine theta over cosine theta. Well, we know what sine theta is. Sine theta was given up here as 5 over 13. It's given right here. So that's 5 over 13 divided by cosine theta is negative 12 over 13. So we flip and multiply. So 5 over 13 times 13 over 12, and that part's negative. So the 13's cancel here and here, and we get tan theta is 5 over 12. That's our answer, and it would need to be negative. We're in quadrant 2, so tangent is negative there. Negative 5/12, final answer. Okay, the second example here, if Q is a rotation angle that terminates in quadrant 1, so that's important, that means all the trig values should be positive, and tan Q is equal to 3, find secant Q and cosine Q. So Q is the variable for our angle in this case. So we want to find an identity that puts tangent and secant together, because if we can find that and find secant, from that we can find cosine, because secant and cosine are reciprocal. So we'll be using a Pythagorean identity first. It's this one here. Why this one? Because it includes tangent and secant, two of the given, one of the given and one of the unknowns. So that's how we choose that identity. And then from the secant value we can get cosine using the reciprocal identity that says that secant and cosine are reciprocals. So we need to fill this in. If tan Q is 3, then tan squared Q would be 3 squared or 9. So we'll write it this way. 1 plus 3 squared equals secant squared of, in this case, Q. Q is our variable for the angle. So 1 plus 3 squared would be 10. 1 plus 9 is 10. So 10 equals secant squared of Q. So to find secant Q, we need to square root both sides. So we get the square root of 10 is equal to secant of Q. The squared falls away when I square root it. And it would be plus or minus, but we're in the first quadrant, so all the values are positive. So square root of 10 is the answer there. So if secant Q is the square root of 10, then cosine Q would be the reciprocal of that. Realize this is over 1. So cosine of Q, we just take the reciprocal, is 1 over square root of 10. We should rationalize this denominator, so we'll multiply by square root of 10 over 10, and we get we are multiplying by square root of 10 over square root of 10, so this gives us square root of 10 over 10 for cosine of Q. So those are our two answers, square root of 10 and square root of 10 over 10. All right, this next section for simplifying trig expressions, it says write each expression in terms of sine and cosine and simplify, and that's very common. You generally want to use your identities to rewrite everything in terms of sine and cosine where possible, because that will help you with the simplifying part. So tan of x is equal to sine x over cosine x. That is from our list. That's this identity right here. So we're going to be applying that right away. So cosine x, tan x would be, let's put an x here, times sine x over cosine x. Once we do that, we need to simplify. So this is like cosine x over 1 times sine x over cosine x. Well, the cosine x's would cancel. We'd get sine x over 1 or just sine x. So cosine x tan x simplifies to sine of x. This one would be similar. Let's look at this one. Secant x times cosine x. Secant x, using the reciprocal identity, is the same thing as 1 over cosine x. So multiply that by the cosine x here. That's this cosine x. Put it over 1. These cancel, so you have 1 over 1 or just 1. Let's look at this one here. So we want to rewrite everything in terms of sine and cosine. So we would get secant x is 1 over cosine x divided by, I usually write it this way, that's the divide right there. Cosecant is 1 over sine x. So we're dividing two fractions, flip and multiply, so we get 1 over cosine x times sine x over 1. which gives us sine x over cosine x, which gives us tan x. So we just applied this tan x quotient identity right here in the final step to give us the answer. So this is simplified. You want to try to get rid of any fractions. You know you're simplified when you don't have any other fractions left, and in general you should be writing them in terms of one of the trig functions. So tan x is the simplification there. Let's do one more quickly here. Let's do g. So rewrite everything in terms of sine and cosine first. So sine x. Cotangent x, same thing as cosine x over sine x. That's one of those quotient identities. Look at your list if you need to see it. Secant x, same thing as 1 over cosine x. That's a reciprocal identity. So let's cancel what will cancel. Sine x there, this is over 1. Sine x cancels with that sine x. Cosine x cancels with that cosine x. And we're left with 1 over 1, or just 1. So final answer on G would just be 1. Okay, for part 4 here it says, if necessary, multiply or divide to rewrite each expression and check to see if any Pythagorean identities apply, then simplify. So a general rule of thumb is if you see a squared term with your trig expression, you probably should look in the Pythagorean section because you can probably simplify. And we're actually going to be using this one right here and this one right here in this same problem. So first, sine squared x plus cosine squared x equals 1. We're going to use that first. So we have that right here. Sine squared theta plus cosine squared theta is 1. So we're left with 1 plus cotangent squared theta. So I replace this with that 1 right there. And then that's all over the cosecant theta. So 1 plus cotangent squared theta, if you look right here, that's cosecant squared theta. So this equals cosecant squared theta over cosecant theta. So you have a term squared over itself, so basically this cancels with that square there, and you're just left with this cosecant of theta. And you're in terms of one trig function, no fractions left, so we're going to call that simplified. Cosecant theta is the answer there. Let's look at one other one. Look at D here. So we have sine theta plus cosine theta all squared, that whole quantity squared. Subtract 1 all over cosine theta. So I'm going to do some work up here. So we need to FOIL this out. So we have this sine theta plus cosine theta times that same quantity, sine theta plus cosine theta. So when we FOIL that out, we get sine squared theta, and then sine theta cosine theta plus sine theta cosine theta, and switch colors here, cosine theta sine theta there, and then cosine squared theta there, all over cosine theta. See, that was, I need to subtract 1 here, that's this minus 1, and then cosine theta is in the denominator. So we can combine some things. This would become 2 sine theta cosine theta, and sine squared theta plus cosine squared theta equals 1. So I'm going to make this piece and this piece into 1. So coming over here, 1 plus 2 sine theta cosine theta minus 1. So what I did here is I just put one of these together with one of these. Remember, this is a sine theta cosine theta, this is a cosine theta sine theta. They're the same. The order is different, but you're multiplying, it doesn't matter. So there are 2 of those. That's where this is coming from. And again, this plus this gave us this 1 right here. And then we had this subtract 1 here, which is this negative 1. So those cancel. 1 and negative 1 cancel. So we're left with 2 sine theta cosine theta all over cosine theta. And now this cosine theta goes with that cosine theta, and we're left with 2 sine theta. And we're in terms of one trig function, no fractions left. So on part D, 2 sine theta is the final answer.